yesterday we ended on electron affinity, and my question to you was, when we began this little part, is what does affinity mean? And that is to love or to like. So, electron affinity is the ability of a neutral atom to gain an electron. Okay? Now, when you gain an electron, there must be some sort of energy change. And so when it gains that electron, there's going to be an interchange, and we're going to try to determine which ones have a higher affinity for some electrons than others. Now, here's the deal. If you love electrons, are you going to easily take them and require very, very little energy? Yes, okay. Which group do you think is going to be that group? 17. All right, so there are also elements out there that hate them. They don't want them. But in the chemical world, can we force them to take one? Yes. Would that require energy? Yes. If I make you accept an electron, am I going to have to put energy in? So am I going to use it up? So what would happen to my energy value if I'm using it? It's going to go down, right? So do you agree that will become a negative value? All right, so keep that in mind. All right, we talked about that yesterday. We talked about this yesterday. And so let's get to this. I'm telling you now, you are going to see one of these formulas on the test. You're going to see one of them. Okay? Let's talk about the difference. Let's start with the electron first. Look in both formulas. Do you agree that the electron in both of them, let's try that again because you can't see that. Do you agree that the electron in both of them is a reactant? Okay? How do you know it's a reactant? It's on the left side of the arrow. So very good. So the electron is a reactant. All right. Now, let's look at the letter A next. The letter A on the left side of the reactions are both neutral. How can you tell they're both neutral? There's no positive or negative. The first one. Okay? Matter of fact, let's just do this. Let's do it in white. So that A and that A. They're both neutral, right? Now, look on the right side of the arrow. We have this A and this A. What signs are they? What? They're negatives. So they have gained or lost an electron. Gained. What do we call that ion that's negative? An anion. So both of them have become anions, correct? What is the difference in both of these formulas? What is the difference? It's where the energy is located. Do you see that? All right. And the top one, the energy is a what? Very good. So, losing energy means that it is a product. Energy is a product when you lose it. There's another word we can use in here, and it's energy is released. Energy is released. Okay? Everybody go with that? Now, how do we know that this is an exothermic reaction? Well, duh. But what did y'all say? Because it is released. That is what I'm trying to get you to see. There's two other things I want you to see. What does the letter H represent? Enthalpy. And what is enthalpy? Ooh, look at y'all. So, delta H is enthalpy. If it's exothermic, does anybody remember the sign? Negative. Very good. Exothermic. Does it get hot or does it get cold? It gets hot. Now, is hot relative, which basically means what's hot to you, maybe not hot to me. So it could, if it goes up 2 degrees, did it increase in temperature? Yes, that may not be hot, but whatever. We just know it's going to get a little warmer. Yeah. Hot and cold are relative. It could be 1 degree up or it could be 1 degree down. But did it change temperatures? I don't feel like doing that today. All right, so, but here's the deal. energy, if it's endothermic, energy must be added or absorbed. Very good. Okay, so if it's forced, energy is going to become a reactant. Do you agree that I'm using my energy in order to make you take that electron? Very good. Now, which groups want to take an electron and you don't even have to force them to? Very good. So we can put group 17 right here. Which group is going to fight you and fight you and fight you to take one? Groups 1 through 13. Okay? They do not want an electron at all. You're going to have to force that thing on them, and they're not going to want to do it. So the last little thing we can add, if it's endothermic, delta H was what? Positive, and it's hot or cold? Cold. All right, so that's the last thing. So electron affinity values can be positive, and they can be negative. If they're positive, it's exo, and if it's negative, it's endo. Okay, the more negative the number, the higher the affinity. Okay, the more negative the number, the higher the affinity. I think I just did that. Okay, all right, so according to this chart right here, where are the highest affinities? Not noble gases. Because the halogens, very good, group 17. Why are the noble gases not included in that? They don't want to react. They don't want any of the electrons, okay? Now, are there some situations where instead of it going up, it actually kind of goes down just a little bit? Those are the oddballs. We don't worry about those. But as a natural progression, does it trend to go up? What is the natural trend as we come down? It gets a little bit shorter as we come down towards the end of the periodic table. So again, that's kind of the trend as we see there. All right. Again, we can kind of skip that. And we said the more negative, the more love. Who has the highest negative value? Yep, highest negative value. Who specifically, though? Chlorine. So they have the most love. That's all. That's real sweet, right? So, that value, that's the electron affinity value. Okay? So chlorine has the most love for its electrons. It's going to do whatever it takes. All right, now, we've said that it could be positive, but there aren't any positive values on this table. Who hates electrons the most? Who? Number-wise. Well, you can't really talk about nitrogen. I don't really know why that's negative or zero, to be honest with you. Who has the least? Boron. Boron hates electrons. It can't stand them. It wants to get rid of them at all costs. Okay? So again, that's kind of how you can look at this chart. Okay? It is. If you think about it, it's already got 3. It doesn't want another one. Does that make sense? Okay. All right. Electronegativity. This is the last and final topic. Up here, I want you to write this. All right. I told you a long, long time ago that I'm going to try to translate some of these elements into bullies, and I'm going to try to translate them into nerds. Okay? But first of all, we need to talk about electronegativity. It's a long syllable word. Okay? I call this the big ugly word. I don't know why, I kind of got in a habit. Electronegativity. So here's what we need to talk about. Valence electrons. Where are they? The outermost orbital, right? Hold together, valence electrons hold atoms together in a chemical compound. What is another word to make chemical compound easier to say? In a bond. Okay? Valence electron hold atoms together in a chemical bond. So, if you have A and you have, atom A and atom B stuck together, First of all, what's holding that? What is it called when they're stuck together? A bond. And what's holding that bond together? Valence electrons. Okay. In many compounds, the negative charge of the valence electrons, first of all, how do we know they're negatively charged? Electrons are negative. Is concentrated closer to one atom than the other. That is the most important thing that you can understand whenever we're talking about this. So, one more time. In many compounds, the valence electron is concentrated closer to one atom than the other. That's what electronegativity boils down to. What does it mean to be concentrated? Okay, I want you to circle concentrated and write this. Found more often. Okay? So, at break, where are most of the students concentrated at? In the commons area. During class time, where should the most concentration of students be? In the classrooms. So, when two atoms are bonded together, one of the atoms will take the electrons and pull it closer to it. One of them. Okay? And we're going to talk about how we know which atom it is. Alright. Linus Pauling. You do not need to know his definition, but he was the first person to describe it. This is what he said. The power of an atom in a molecule. Let's highlight the word molecule, and I want you to write this. Another word to say molecule. Bonded atoms. Okay? So if you're in a bond, do you have to have more than one atom? Kenzie, you with me? Okay? Bonded atoms. The power of an atom in a molecule to attract electrons to itself. And I have a very simple way of explaining this. Tug of war. If you and I were to play tug of war, who is more likely going to win? You better say me. Okay? Alright. It was a joke. So the point of emphasis is the rope is going to represent what if we're a molecule? The electrons. And those electrons are part of the bond, right? So what are we constantly doing in tug of war? Pulling those electrons back and forth. What if you were in tug of war with yourself? Who would win? Yourself would win. But really, what would happen? It would balance out, right? Nothing would go. Now, would the rope still move? Yes. It's not going to be stagnant. That's what we got to understand. Are electrons stagnant? What does stagnant mean? Never moving. It's going back and forth. But in the end, what happens to the movement back and forth? It balances out. The net movement would result in no change. Does that make sense? All right. So, we've got to determine when we have atoms bonded together, who is going to win that tug of war. And so here's the new definition of electronegativity. Electronegativity is the measure of the ability. What does an ability mean? Able to do something. So which one has the ability of an atom in a chemical compound, what's another way to say chemical compound? A bond, to attract electrons from another atom. And in a way, I want you to kind of think about this. Attract electrons is we're going to really be talking about sharing them. We're going to talk about the ability for Amaya to things to be attracted or not attracted. Okay? So, here is the most important concept about the atoms themselves. Here's a trend, and we're going to go into the trends in just a second. Electronegativities tend to increase across a period. So as I move left to right, What does that tell me is happening to the values? They're going up. So are they getting stronger or weaker? Stronger. So as we move left to right, they're getting stronger. Now, remember, these atoms must be in a compound. Okay? Must be in a compound. Now, as we go down a group, so as if I'm in group 1, as I go lithium, sodium, potassium, rubidium, it decreases or remains about the same, but really, we want to know that it decreases. Why do you think it decreases? What's happening to those atoms as we go down? They're getting what? Very good. So as we go from top to bottom, they are weaker because they're bigger. Now, I know what you're thinking. Wait a minute, you just talked about tug of war. Whenever you play tug of war, what do you always want? You always want bigger people. By the way, if you ever play tug of war, do not put your biggest, strongest person in the back. Put them in the front. Why? There is a lot more leverage at the front of the rope than there is at the back of the rope. Okay, that's a physics thing. Always put your strongest at the front. Never put them at the back. So, as we go top to bottom, they're getting weaker. So because they're getting bigger. But I know that's kind of backwards of a concept of life. But think about them being so big and so fat and so slow that they can't really move. Okay, and so that's kind of what's going on here. A numerical scale. What does it mean to be a numerical scale? It's a number, okay? It's a quantifiable number. A number based upon a physical measurement allows a comparison between the atoms. This is what you need to know. Who is the most electronegative? Fluorine. So this is what I want you to put beside fluorine. He is the biggest bully. He is the big, bad, bully gangster. Fluorine. He's your guy. So if you ever match up with fluorine, are you ever going to beat him? No. He is going to win this race. He's going to win this tug of war. Now, numerically, its quantity is a value of what? 4. So everything else must be what in comparison to 4? Less than 4. Everything else has to be less than 4. All right, so is everybody good with this? So if we know that fluorine is the strongest, according to the periodic table, who do you think is going to be the weakest? Remember, it gets weaker as we go back to the left, but also as we go down, what happens? Francium is your weakest. It's the biggest, nerdiest old man you could ever think about. He is blubbery fat and, just gross. Okay? He is your biggest nerd. He is such a nerd that he actually comes to you at lunch and says, "Do you want my lunch money?" That's how easy it is to take his electrons. Okay? All right. Now, one more thing that we need to talk about is this. The closer an atom is to fluorine. Now, what do we know about fluorine? He's the biggest bully. He's the most electronegative. So the closer you get to fluorine, the greater the electronegativity comes. So who are the two closest to fluorine? Oxygen and chlorine. Those are the two closest. Now, why? Yeah, do me a favor. Hand me that whole stack. Just take you one. Okay. Count how many you need and pass them back and then pass them over. Don't pass them all the way back. Okay. All right. So notice what group we haven't mentioned yet. Why have we not mentioned the noble gases? Okay. When do we calculate electronegativity? It's when they are what? They have to be in a bond. Do noble gases bond? No. By the way, that's a little small white lie. We'll talk about that later. Okay. So again, we'll get that next chapter. So again, as we get closer to fluorine, the more electronegative they are compared to atom farther away. The greater the electronegativity difference between an atom and a bond, this is probably one of the most important concepts that you're ever going to learn in this chapter right here. I'm begging you to please know this little thing. the greater the difference between the atoms, what happens? Hang on, don't pass them all back. Don't pass them all back. Count how many you need, pass them back, and then pass them over. Okay. So the greater the difference between two atoms, the more what does it become? Polar. This is the word you need to know. Polar is very, very, very important. Okay? Polar. What does polar mean? Opposite ends, but very good. It creates different charged poles. Creates different charged poles. And what do you think the charges are going to be? Very good. They're going to be positive or they're going to be negative. Now, which pole do you think is going to be the positive pole? The one that gains or loses the electron? Loses the electron. Which one do you think is going to be the negative pole? The one that gains it. All right. So here's what I need you to do. I need you to add a page below the slide. Okay. Add a page below the slide. Yes. Charged poles. All right. So here's what we're going to do. We're going to take this thing right here. What is this thing that I've just written? Okay, it's diatomic hydrogen. Very good. Diatomic hydrogen. Everybody okay with that? All right, so here's what we're going to do. We're going to take hydrogen and we're going to bond it with itself. So here's what I need you to know. That one line equals one bond, which equals 2 electrons. Okay? One line equals one bond, which equals 2 electrons. Yes, sir. I don't know, but I'm fixing to add a lot to it. Is everybody good with that so far? If these two H's were to get in a tug of war, who would win? Obviously H. Which H? Neither H. All right. Now, what was that value that fluorine has? What was its numerical value? 4.0. So let's stop for just a second. Guys, this is for future. Anytime you see me write that, what do you think it stands for? Electronegativity. I hate writing that whole entire word, so that is my shortcut. You'll never see that in a textbook. You'll never see it on anything else, but that's my shortcut for it. Trust me, you'll appreciate that shortcut. Now, hydrogen has a value, and we're going to talk, and I'm going to show you what it is. Okay? You stay where you are. I'm going to change pages, and I'm going to scroll down a few slides to right here. According to this chart, what is the numerical value for hydrogen? Everybody see 2.1? Okay. All right, so hydrogen's value is 2.1 minus 2.1 gives me an answer of 0. So, is there any difference in their electronegativity values? We cool with that? So, here's what's going to happen. Remember, our electrons stagnant? What are they constantly doing? Wait, what? They're pulling, but they're moving. Electrons are constantly moving. So here's what's going to happen. We're going to try to determine exactly what this electron is going to do. So once it goes around this, where else is it going to have to go? Around the other one. So do you agree that eventually a pattern like this is going to develop? Now, why is this electron not spending more time around one of these H's than the other? Because their electronegativity values are the exact same, right? So do you agree that we can quantify this as equal sharing? Do you agree that's a fact? There is something we call this when it is equal sharing. A minute ago, the last bullet that we covered, the slide right above this, we said the greater the difference between atoms in the bond, the more polar the bond. Is there any difference in electronegativity values? So we would not call this molecule polar. What will we call it? Say it again. No. Non-polar. It's non-polar. Go back and read the definition that I gave you for the word polar. What was the definition I gave you? Different charges on each end. Do you see any difference of charge on this thing? Do you agree there's no difference, right? So we're going to call this thing non-polar. Guys, I'm teaching you chapter 6 right now. We're in chapter 5. But all this should make sense. It's all going to tie together. All right, now we're done with H2. We're going to go ahead. No. Electronegativity will, but this part will. Okay? So, we have HF. Sir. Friday. It's Friday. Okay? All right, HF. I mean, today's Tuesday. I know. All right, now what have we just done? Are they the same? What do we know about fluorine? He's the biggest, baddest bully on there. He's the most electronegative. So here's the deal. We have fluorine. What was its value again? 4. Very good. 4.0. Hydrogen has a value of 2.1. So what is the answer to that? Very good. 1.9. Now, in this chapter, you will not have to do this. In chapter 6, I'm going to teach this to you. When you do this math, there is a range in which it will tell you the bond type. We're going to hold off on that for just right now. Now, one line equals one bond, which equals 2 electrons. So this time, we're going to talk about that same electron. When it starts moving, who is going to win this tug of war? Fluorine. So do you agree that electron is going to spend more time around the fluorine? So this is what's going to happen. No, there is not a certain number of times I'm spinning this thing. I'm trying to make an emphatic point that the electron obviously does what? It spins around fluorine a lot more often. Okay, sir? It's higher number always on top. Basically, you want a positive value. Okay? Now, is this equal or unequal sharing? Definitely unequal. Definitely unequal. Have we just created different poles? Yes. What do we call that thing when it has more than one pole? Polar. Wow, look at you guys. You guys are smart. All right. Now we have, sir. Yes, it would have the largest difference. Okay? So, we've got to now define our poles. Which pole, the hydrogen or the fluorine pole, is going to be the negative pole? Which one has the electron around it more often? Fluorine, so it's going to be more negative, right? Now, this is going to be weird, but I need you to do this. Make this little symbol. It looks like an S with its tail touching or an 8 without its top half. Does that make sense? It's like an S with its tail touching itself or an 8 without the top part. No, I mean, okay. Whatever you need to do to make it look right. Now, I made the fluorine in negative. Do you agree that that's a pole? I made the hydrogen in positive. Do you agree that's a pole? Why is hydrogen in positive? It lost its electron. Now, I know what you're thinking. What is this little S thing? All right, here's what I want you to do. I want you to define this. Write this again. The actual symbol is actually the lowercase delta symbol. What is the capital delta? It's a triangle. This is the lowercase. Okay? And what it stands for is a partial or a slight charge. What does it mean to be partially or slightly? Not all the way. Do you agree that that electron didn't go all the way to fluorine? So it's partial. It kind of goes back and forth. All right. So we clear on all this. So does this make sense? If it's unequal sharing, it's going to be partial. Ionic is when we get to turn into an ion. Ionic bonding forms ions. And what is the definition of an ion? A gain or a loss completely of an electron. No, we'll talk about that. No. You're overthinking it. Any questions? Sir, you got it? Okay. All right, so now let's go back and let's look at this chart. Obviously, where is the highest electronegativity? Fluorine. Well, we know that obviously that fluorine is the highest, but there is a group that we left out, and we left them out. Why did we leave the noble gases out? They don't react. And again, I told you this a minute ago, that's a little white lie for right now. Again, for right now, that's a little white lie. Obviously, where is the least electronegative? Way down here by francium. Again, so you have the biggest, baddest bully on the block in fluorine, and the weakest, fattest, slobberiest old man down here in the bottom left. Okay, so do you see the trends? Obviously, are there a few oddities right there in the middle? Okay, but do we need to know the oddities? No, I don't even know what they are either. Okay, so there's no point knowing. We just need to know a general trend. Okay, where's the darker color? Way up there at fluorine, right? Okay, and as we come bottom left, it gets wider and wider and wider. So that's going to be, this is called the Pauling scale. Remember, Pauling was the first guy who talked about electronegativity. All right, here's your numerical values. This is something that you're going to get in the next chapter. You're going to have this exact same picture, and I may actually print it out and give it to you so you can use it. All right, so that's the trend in electronegativity, and this is, in essence, the entire next chapter summed up in one picture. There are three major bond types. You should already know two of them, ionic and covalent. What is the third type you've never talked about? What is a metallic bond? A bond between metals. Wow, that's hard stuff right there. Okay, I do want you to write this underneath metallic, and we'll talk about it next chapter. Please write this down. Called the sea of electrons. A sea of electrons, like the ocean sea. That's a great, great question. A hydrogen bond is not a bond. Why they named it that, us chemists nowadays are furious with them. It is really an IMF, and we're going to talk about IMFs next chapter. Okay, an IMF stands for an intermolecular force. Inter means between, molecular means molecule. It is a force between molecules. Do you agree that this little brown thing is a molecule? If I had another one, it would be the thing that held them together. Water is a molecule. It's what holds water molecules together. Okay, we'll talk about that. So, now, here's the issue. Ionic bonding. Ionic bonding comes from what? Ions. Wow. What are ions? No. They gain or lose electrons. So, do you agree that they are fully charged? Yes, no? Because they gain or lose electrons? If you lost your iPad, did you fully lose it? You can't lose half of it. Right? It will be in my heart. Yeah, right. So here's what I want to talk about. So we know that over here, How can I tell that that is an ionic bond? Does it have a full negative and a full positive? Are those two atoms, or those two ions completely separated in terms of charge? You can tell that they're separated. Okay? So, this, over here, again, is an ionic bond. Now, this is the new part that you may not have learned in 8th grade. There's actually two types of covalent bonds. What are the two types? Polar and nonpolar. This is what I want you to do. Beside the word polar, please write the word unequal. And beside nonpolar, what would you write? Equal. Very good. Now, we're going to have to add this word somewhere because it's not going to fit into here. But I want you to write the word covalent. And we're going to add something behind it. If I said that you coexist, or you cooperate, or you co-teach, what are you doing? You are doing responsibilities with each, like you have an equal responsibility, right? Valent. Valence. What are valence? Electrons. When you bond, what does the bonding? The valence electrons. So what does covalent mean? The sharing of valence electrons. So does that work? Does that make sense? So covalent means the sharing of valence electrons. Now, how many of you have an older sibling? Okay. How many of you equally shared your toys with your older sibling? And if you do, you're probably lying. But you aren't very far apart, though. That's fair. Okay. How many of you had a mean older sibling that always took your stuff? Abby, I believe it. I've got a brother that's 6 years older than me, and let's just say it wasn't very fair. So, sharing is an arbitrary term, right? Because what are the two types of sharing? Equal and unequal, which means polar and nonpolar sharing, right? If you're lucky, if you have an awesome sibling, you probably had nonpolar equal sharing. Mary, you and Teresa get along that well? I'll take that as a no. But again, if you don't, you probably have an unequal sharing. And so this is what this part right here is going to represent. Polar covalent. What is that little S-looking thing again? It's a lowercase delta, which stands for slightly or partially. So do you agree that they're kind of going back and forth right there? Okay, so it's an unequal sharing. Well, what do we obviously tell about this far left molecule? It is equal sharing because they're going back and forth. And the one thing you notice is what is not present. No poles. No poles. There's no positives or negatives anywhere all around that thing, is there? All right, the last thing in that picture I want you to notice is this part right here where it says electronegativity differences. How can you find those numbers? That scale that I gave you, and you'll just subtract them. We'll learn that in the next chapter, okay? In saying that, using the electronegativity values, you can find the difference between the two elements. Trying to make a chemical bond will tell you which type it will be. Does anybody remember the value that was between fluorine and hydrogen? 1.9. Where would it fall on this scale? Between 0.4 and 2.0. What type of bond was that? Polar covalent. Is that exactly what we said it was? Okay. What was the difference in the hydrogen and hydrogen? Well, notice what? It's 0 between 0 and 0.4. Do you agree that it just looked just like this? Okay. And we're going to get into ionic a little bit later. Okay. All right. So just kind of keep that in mind. Now, the electronegativity difference, do me a favor and write the word math above this. Okay? Do you agree that you could do some math and subtract some numbers? If there is 0 difference, do you agree that would give you equal sharing? Now, there actually needs to be one other word. If you have equal sharing, what kind of covalent was that? Non-polar. Please write that above the word covalent. If it was equal sharing, and again, how are we getting this? Based on the difference in electronegativity. If there was intermediate sharing, is that equal or unequal sharing? Okay. Well, when it's unequal, what do we call that? We called it polar. Okay. If there's a large difference, you lose or gain an electron. Well, when you lose or gain an electron, what do we call that thing? An ion. And ions have what kind of bonding? Ionic bonding. So is all this making sense? Guys, you already know chapter 6. Okay? But we still, and all this is going to come from this information. No. Okay? All right. Now, last little thing I want to talk about, these electrostatic potential map. What? Dude, this is chemistry. Nothing about Dragon Tales is... I have no clue what you're talking about. No, I have no clue what you're talking about. I've never seen it nor heard of it. Alright guys, I want you to write that down for me, please. Again, once you know this will make this stuff kind of make a whole lot more sense. If it is a red color, you have a very, very high concentration of electrons. Okay? What does it mean to be concentration? What is concentration? Having, very good, it's abundant in one specific area. If you go to McDonald's and get their sweet tea, what would you call that, concentrated or not? Why is it concentrated? It's a whole lot of sugar, right? Okay, it's a lot of sugar in that one cup. So, if we have a high concentration of electrons in the red area, then what does that mean the blue has to be? Low concentration. Now, do you remember when I drew that diagram for you a minute ago? Does this kind of match up with what I just drew? Wasn't those red circles more around the fluorine end? Yes? Okay. Basically, this is a beautiful, wonderful computer image of what I drew. Okay. This is how they actually do it in the chemistry world, and I figured it would just show you some justice of exactly how it works. Okay. Now, is this equal or unequal sharing? This is totally unequal, right? So, since we have unequal, is that polar or not polar? Very good. It is going to be polar. Now, when it's polar, you have to have poles, right? Polar means poles. What are the two signs of the poles? Positive and negative. If the red is a high concentration of electrons and the blue is a low concentration, where would the partial negatives be? The red or the blue? The red. Why the red? Because that's where the electrons are located. Well, if the red is a partial negative, then what is the blue? Partial positive. Very good. And again, it's partially positive because the electrons are spending more times around the other end. Now, I also want to show you this on my drawing because it's a little bit cooler to see it this way. I want you to see according to this molecule, what is this molecule? It's water. This is water. If if hydrogen and oxygen were to get in a tug of war, who would win? Why oxygen? It's more electronegative. How do you know oxygen is more electronegative than hydrogen? No. No. Who's it closer to? Fluorine. Very good. It's closer to fluorine, so it's more electronegative. So, do you agree that this right here would happen? I would have an electron that would do this, right? Okay. What's going to happen to this other one? Same thing. And so you get what shape? You get Mickey Mouse. Okay. Now, did you really spell mouse with an E in the beginning? That's Mosi. Now, here's the deal. Do you agree that there are two different bonds in this one molecule? Okay? Do you agree that this hydrogen is going to be partially positive? Why? Because the electrons are going away from it, right? What about this hydrogen? Also partially positive. Go ahead. Yeah. What about this oxygen? Not fully. It's still partially negative. But here's the difference. How many electrons was it sharing unequally? 2 partial negatives. Does that make sense? No. Because it's still not completely taking them. It's still sharing them. So on the part that you have, do you agree that this is the picture that you have down here? This is what I want you to do. I want you to say that this is partially positive. This down here is partially positive. But this is 2 partially negatives. So what do you think would happen if you had an atom that was bonded with 3 other atoms that it was taking its electrons? What would it be? Well, I'm glad you said that. Let's look at our next example. What is this compound right here? This top one. What is the formula? Very good. It is NH3. What is the name of NH3? Anybody know what it is? No. There's no nitrate. It's ammonia. Okay? Where have y'all heard of ammonia before? And what? Did you just say a sickness? And cleaning. It is a cleaning compound. Now, according to our electrostatic potential map over there, where are the highest concentration of electrons? At the top, bottom, left, right? At the top. So most of your electrons are going to be way up here at the top, right? Well, what did all of those, or what did that nitrogen do with those hydrogen electrons? Didn't it take it in? Why is nitrogen more electronegative? It's closer to what? So now, how many did it take? It took 3. So up here, right, 3 partial negative, and each hydrogen is still what? Partial positive. Okay? Now, the bottom one looks a little weird. Why does the bottom one look a little weird? It's kind of like those two. First of all, what is the compound formula? Formula. CO2, and what is CO2? Very good, carbon dioxide. Now, guys, do y'all recognize that these shapes look quite a bit different? The next chapter, chapter 6, we're going to learn about how to draw these shapes. Okay? Now, according to this electrostatic map, where are the electrons located? Where are the highest concentrations? On the outside, right? So, we've got a partial negative here and a partial negative here. Where's the partial positive? In the middle. But how many partial positives would you have? 2. Very good. So we have 2 partial positives sitting in the middle. Okay? All right, so is this starting to make sense a little bit? About how electronegativity makes it different? Okay, all right, this is the last picture. We're not going to go any. I'm just kind of want to show you these. HCl, obviously, where's the big negative? Where's the negative end? On the right end. H2S, where's the negative end? On the bottom, SO3. On the outsides, right? And then methane, it's kind of in those weird in-between areas. So again, these are just, and this will make a lot more sense in the next chapter. All right, so the final review, and we're done with the notes after these next 2 pages. Okay? All right. The one thing I want you to add a few things to this page. We haven't talked about metallic character yet. It's going to be in the next 2 or 3 slides after this, but what is metallic character? How much it acts like a metal, right? We're going to talk about that. Where are all the metals located according to the stair-step line? To the left, right? So, is it really, really metallic as we go left? Okay, just keep that in mind. So, the atomic radius and ionic radius decrease as we go left to right. Why does it decrease? Because the Zeph does what? The Zeph goes up. Everybody okay with that? Why does it increase as you go down? You have more orbitals. Okay? Now, notice down here. Ionization energy, electron affinity, and electronegativity. Do you agree that they have an opposite trend than the top 3? Okay? So they increase as we move left to right, and they decrease as you go down. Okay? But basically, it's the same reasonings. It's just a different trend. Okay? Because the size gets a little bit smaller, and the smaller it gets, do you agree that it's harder to take its electron? The bigger of a bully it becomes, and the more it loves its electrons, the smaller it gets. And so that's why it trends that way. All right? If you like this picture, you can use that one. That's up to you. Again, it does not matter. All right, the last thing, metallic behavior. Metallic behavior increases left and down. Metals tend to lose their electrons. Why? They have lower ionization energies, and they want to become stable by losing their electrons, okay? Highly metallic elements are likely to make positive ions, and then that's the metallic thing. And this is the last question, and we're done for the day. Predict of those 3, gallium, bromine, and calcium. Write it down. Don't yell it out loud. Write it down. Which one of those 3 will have the highest electronegativity, and then explain it in terms of periodic trends. You should have a periodic table right there in front of you. See if you can answer that question. The ability of an atom in a bond to attract electron closer to itself. No, it really doesn't fall under Zeph, because Zeph is within each atom itself. Yeah, it is not Zeph. Alright, how many of you said gallium has the highest? Have you said bromine is the highest? Okay, how many of you said calcium? It is bromine. And here's the reason why it's bromine. All of them are in the same period. They're all in period 4. Bromine has the highest atomic number and is farthest to the right. We know trend-wise, as we move left to right, our electronegativity goes up. So bromine should have the highest electronegativity because electronegativity increases across the periods. And also what? Nope. What is it closest to? It's closest to fluorine. There's your other possible trend. And that is the end of chapter 5.